Good morning. This video is for functions. So a function f from a set x to a set y is a rule that assigns each element x in x to a unique element y in y. So if we have a rule which assigns a unique element x in x to a unique element y in y, we call f a function. Right. So the set of input values are the domain values. Then the set of output values are the range values. So the range and the domain are sets. The domain is the set of input value and the range is the set of output value. So I'd like you to consider a function as kind of a machine. Right, you're gonna put like a function as a machine where you input your products here, and you get you expect to get the output here. So we're going to take this one as our domain, inputs, domain inputs. And this one is the range output. The kind of the output. So input domain values to output the range values. That is a function. So the domain values are those values that keeps our function defined. Right. For example, if we have 1 over x, if x is equal to 0, if x is equal to 0 on this one, you really know that if x is equal to 0, we have 1 over 0, which is equal to infinity. So that one is not defined at x is equal to 0. So the domain should exclude, x is equal to 0. Just as an example, maybe let's just have a function like f of x is equal to 2x plus 1. The domain of this function are those values in R. So just for better understanding, let's just take some points in R which we can input here. So let's say we take 1, 2, 3, 4 in R. We just want to input them. So the set of 1, 2, 3, 4 which are in R, if we say f of 1, we get 2 by 1 plus 1. this is the input, this is the output. So if we input 1, we output 3. So f of 1 is equal to 3. So basically, if we are relating this to the Cartesian plane, you can actually see that the y values generally are output values, and then the x values are input values. So whenever you are asked to find the domain of a function, you have to find the values which keeps the function defined. That is what you should find. You should always find the values which keeps the function defined. Okay, so let's now work out some questions on the domain of a function. Okay, so I just took these questions from our tutorial sheet. So the question reads, find the domain of each of the following: 1 over root of 1 minus x. So for us to find the domain of these, we have to exclude all those points from our domain, which makes the function undefined. So we know that this one, like the denominator, our denominator should not be equal to 0. So we know that square root of 1 minus x should not be equal to 0. That is what we know. And also we know that for it not to be equal to 0, we need to have 1 minus x being greater than 0, right? Since under the square root, if you put anything which is less than 0, we get a complex number. Yet in calculus, like in this topic, we are not going to be considering complex numbers. So this one implies that x is greater than, sorry, x is less than 1, which means our domain can be written as x is less than 1, or x is an element of minus infinity up to 1. Then for the second one, we know that under the square root sign, for a function to remain valid under the square root sign, we should have x over 2 minus x being greater than 0. So x over 2 minus x should be greater than 0. And this means that we have to solve this inequality. Okay, so to solve this inequality, we need to use this table. Yeah, there are many methods to solve it, because it's an inequality, so we cannot multiply both sides by 2 minus x. So we have to use either this table or any other method which works. So we want the interval in which this is greater than 0, x over x minus 2. So you can actually see that we tested for x less than 0. For x less than 0, we know that x is negative and 2 minus x is positive. So the outcome here is negative, sorry, because it's negative over positive, so it gives us negative. Then for 0 to 2, we have a positive outcome. And from x greater than 2, we have a negative outcome. Therefore, the region which we want is this one. So we know that for this, our domain is actually 0 is less than x, which is less than 2. And also, the reason why I actually put strictly less than 2 is because of the fact that this 2 minus x should not be equal to 0 as well. So we have to state it here that x 2 minus x should not also be equal to 0. So x is not equal to 2. But this one can be 0. The lower bound, we can consider it equal to 0, and it can work because if you have 0 over 2 minus 0, we get square root of 0, which makes sense. So here it should have been greater than or equal to, and then this fact was going to eliminate the upper bound. I mean the substitution of the upper bound, which just makes it like this. So this one will be 0 is less than or equal to x, which is less than 2. So these two conditions are the conditions we use to find the. Then for this one, this function is valid for all r except when x squared minus 4 is equal to 0. So we don't want it to be equal to 0. So it means that x squared is not equal to 4, which implies that x is not equal to plus or minus 2. So our domain is going to be the set r minus or we can say minus infinity up to minus 2 union minus 2 up to 2 union 2 up to infinity. You can use either way. On the number line, what I'm just saying is we are just excluding these 2 points. Everything else except these 2 points. Okay, so what I was saying is x squared minus 4 is not equal to 0. So x squared is not equal to 4, which implies that x is not equal to plus or minus 2. Therefore, the domain is r minus 2 or minus infinity up to minus 2 union minus 2 up to 2 union 2 up to infinity. Just like that. So the point which we'll be eliminating is minus 2 and 2 only. So you can just find any way you can write which just exclude minus 2 and 2. So you can even state that the domain is all values in R except minus 2 and 2. Okay, so moving back to our notes, there is the concept of a variable and independent variables. So if we have something like f of x is equal to y, Okay, so this one is the x is the independent and y is the dependent. Yeah. So this is a diagram which explains what a domain and a range are. So this one is our input values, which is mapped to a unique f of x, which is the range value. There's an example which is 1 over x. We cannot compute f of 0 since 1 over 0 is not defined. Then the domain f of x is equal to 1 over x, 0 values except 0 of real numbers except 0. So, and if we have example function y is equal to x squared, we have the domain is minus infinity up to, the domain is all values of x in R, which is minus infinity up to infinity. And the range would be now from 0 up to infinity. Just as a little demonstration, you really know that the graph for y is equal to x squared looks like this. So since it looks like that, we'll be having our f of x being greater than or equal to 0. So that's why the range is like this. So if you know the nature of the graph, it's so easy for you to determine the range of the graph. For y is equal to 1 over x, y is equal to 1 over x generally looks like this. That's for y is equal to 1 over x. It looks like that. So the range, you can actually see the range of this. In fact, the domain are x values. X values start from here going upward. So they start from minus infinity up to 0 and 0 up to infinity. Minus infinity, 0, 0 up to infinity. That's for the domain. The range is also starting from 0 up to minus infinity, 0, 0 up to infinity. So for y is equal to 1 over x, that's how it looks like. Then for y is equal to square root of x, we have from 0 up to infinity and 0 up to infinity. If you research about the graph for it, you can just see that it just looks like that. It's almost like that, right? Right, then y is equal to square root of 1 minus x squared. Okay, for this one, we know that we don't want 1 minus x squared to be equal to, we don't want it to be less than 0. So it's either greater than or equal to 0. So that's why you can actually see if we solve this one, we get 1 minus x, 1 plus x is greater than or equal to 0. After solving this using the method which we talked about, we actually see that we have this one, 1 is less than or equal to x, which is less than or equal to 1. Yeah, that's for the domain. Minus 1 is less than or equal to x, which is less than or equal to 1. You can verify this using a graph in which we see that 1 minus x squared is got points on, it's actually a maximum graph. We talked about this in the previous lesson with a maximum graph. So this one is got minus 1 and 1, like for y is equal to square root of x squared. We have minus 1 and 1, and what it means is we want the points where the graph is greater than, or equal to 0. So you can actually see this is the point where the graph is greater than or equal to 0. So you're just going to consider minus 1 to 1. Okay, so likewise if likewise if you are asked to find the domain of this one, we know that we should exclude x squared plus 4x plus 3. It should not be equal to 0. So I would like you to try to find that the domain. But for the range now, you have to use this fact. You have to first let y be equal to g of x. Then you have y is equal to x over, let me just do the shortcut. Y times x squared plus 4x plus 3 is equal to x. So we just multiply both sides by x squared plus 4x plus 3. So we have y x squared plus 4xy minus x plus 3y is equal to new, which gives us y x squared plus x by 4y minus 1 plus 3y squared. 3 is equal to. So for this one to be valid, you have to use the discriminant. So we have yx squared. I'm just going to take it to another screen so that yx squared plus x by 4y minus 1 plus 3y is equal to 0. So what it means is I was actually saying that we use the discriminant b squared minus 4ac. We want it to have solution so it's greater than or equal to 0. So we take y and 4y minus 1 and 3y is our a, b, and c respectively. So we say b squared, which is equal to 4y minus 1 squared minus 4 by y by 3y is, this one should be greater than or equal to 0. So 16y squared minus 8y plus 1 minus 12y squared should be greater than or equal to 0. So what it means is we have 16 minus 12 being 4y squared minus 8y plus 1 being greater than or equal to 0. Then factorization of this will give us the range for our function. Okay, so moving on to monotone and bounded sequence. A real function f is increasing strictly on an interval I if points x1 and x2 in I with x1 less than x2, f of x1 is less than f of x2. So let me just consider some examples. Let's say we have our f of x being equal to 2x or even x or x. So you can actually see that if we have if we have f of 1 is equal to 1 and f of 2 is equal to 2. So it implies that this one is strictly increasing anyway, because f of 2 is actually f greater than f of 1. But I'm gonna talk about also how to prove something generally, and generally prove something I will talk about it in the next section, I guess. So if real function f is strictly increasing on the interval I, if the points x1 and x2 in I with x1 less than x2, f of x1 is less than or equal to f of x2, and f of x1 is less than f of x2. That's a real valued function is strictly decreasing or decreasing on the interval I if for all points x1 and x2 in I, f of x1, x1 less than x2, f of x1 is greater than or equal to f of x2. So the for decreasing is the opposite now. Let's consider, if we consider a function like f of x is equal to minus x, it's strictly decreasing. A real valued function is monotone on the level I if f is either increasing or decreasing. So it's just general monotone if it is either of the two. Then we say that a function is bounded if there is a real valued m which bounds the function. So let's take, for example, y is equal to e to the power of minus x. We know that it won't go beyond this line here. It won't go beyond this line. This line here. So it means that it's actually bounded below by 0. That's e to the power of minus x. Then we can also have a function which is bounded above. Let's consider the function like y is equal to sine x, right? So if we have a graph for sine, it looks like this. This one is 0, this one is pi, this one is 2 pi. You can actually see this function is bounded above and below. That's those are the bounds for our function. So this is just these are just simple definitions of functions. Okay, just to talk about the types of functions. Polynomial functions are functions of that form. For example, we have x to the power of 5 plus ax to the power of 3 minus 2x squared plus 1. Of this one is a polynomial of degree 5. So you just look for the highest power. We can have another example where we have x to the power of 3 plus 2x squared plus 3 plus 3x plus 1. This one is a polynomial of degree 3. So polynomials, you should take note that they should have positive powers on their x values. Otherwise, it's not a polynomial. Then there's rational functions. Rational functions, we've got p of x over q of x. We have x to the power of 3 plus x plus 5 over x squared minus 3x minus 4. Those are like the polynomial over a polynomial gives a rational function. Then we have also power functions. Power functions are functions of the form kx to the power of n, where n is a real number and k is a constant. So we have y is equal to x to the power of half as an example, y is equal to x to the power of a third, and y is equal to x to the power of 2 over 3. Then these ones are very important, piecewise defined functions. So piecewise defined functions now is one function but defined by pieces of functions. Like for this one, we have f of x, which we have f of x, which is actually equal to minus 1 in the range x is less than 0, and it's equal to 0 in the range when x is equal to 0, and also it's equal to x plus 2 when x is greater than 0. So if we could sketch that function, you can actually see that it is minus 1 when x is less than 0, and it is just a dot here. It is equal to 0 when x is equal to 0, and it is also equal to y plus x plus y, x plus 2 when x is greater than 0. So that is a piecewise defined functions. Just for for better understanding, if we could sketch this one, we have something like this. So we have x is equal to minus x for x less than 0. So minus x, we know that the graph for y is equal to x looks is crosses the x like this. So for minus x is like this. So we have y is equal to minus x. It should actually intersect with them. Okay, that's for minus x, right? Then what? Then that is for x less than 0. And then for x in this range 0 to 1, let's just put 1 here. In this range 0 to 1 is exhibiting the graph of x squared. So since we know that the graph of x squared looks like this, it is not going to start, it is just going to start on 0 here and go up to 1. That is what it is just going to do. Then for x equals to 1, so you know that it actually, this one will coincide with f1 here. For x equals to 1, we should have this graph being equal to 1. So we know that the graph for equal to 1 will be just like this. So there should be a corner there. Yeah, so that's how it looks like. So that's a piecewise defined functions. We're going to be using these functions mostly in continuity in the next chapter. There is also transcendental functions. These ones are just like exponential functions, logarithmic functions, trigonometric functions, inverse trigonometric, and hyperbolic functions. There is also what we call even and odd function. So a real valid function, let f be a real valued function of a real variable, then f is even if f of x is equal to f of minus x, symmetric with respect to the y-axis. So examples: modulus of x is modulus of x squared, x to the power 4, cos x, cos x. Let f of x be a real valid function for real variable, then f is odd if minus f of x is equal to f of minus x. So what does this mean? What does this mean? So we have a definition here for even function and the definition here for odd function. So for even, we're actually saying that if we say f of x, we get f of x is actually equal to f of minus x. So it is even functions absorb the negative. Odd functions does not absorb negative values. So like negative, I mean, so even function absorbs the negative, and odd functions exposes the negative. Even absorbs, exposes. So what does that mean? Let's take, for example, here I have some little examples which I have put in place. So you have x squared. If we say f of x is equal to x squared, you can actually see that if we consider f of minus x, we get minus x squared, which is equal to x squared. So this one absorbed the negative value. Same applies with cos or x to the power 4 or modulus of x. We actually talked about modulus of x. Say modulus of, if f of x is called modulus of x, f of minus x is equal to minus modulus of minus x, which is equal to x, modulus of x. We talked about this in the previous chapter. Okay, so the same applies to odd functions. We say the exposes the negative. So by exposing the negative, you're meaning that f of x will be equal to minus f of x. Sorry, That's f of minus x is equal to minus f of minus x is equal to minus f of x. It exposes the negative. So for example, if we take our f of x being equal to minus x to the 3, this one will give us f of minus x is equal to minus x to the power of 3 minus, which is equal to, we have sorry. I had to put this one. Okay, sorry. Let's consider f of x, which is equal to x to the power of 3. So f of x, which is equal to x to the power of 3, we have f of minus x is equal to minus x to the 3, which is equal to minus x to the 3. There is an example, which is f of minus x is equal to, like the example actually requires us to determine whether this function f of x, which is 3x over x squared plus 1, is either odd or even. So if we substitute minus x there, we get, so for us to test that, just substitute minus x. So for you to test whether the function is odd or even, just substitute minus x in the function and check whether the function exposes or absorbs the negative. So you can actually see this one is giving us 3x over x squared plus 1, and this one is exposing the function. So it means that it's an odd function. Okay, so there is combining functions with some differences product. So functions can be combined by adding, subtraction, dividing, or multiplying function. Then there's also composition of functions. Composition of functions, you'll be combining two functions. So let's take, for example, if we have our f of x, which is equal to x squared, and g of x, which is x squared plus 1. If you want to combine f and g, we'll be substituting g of x wherever there was x in f of x. So what I'm meaning is, you really know, like if we're to find, if we have f of x, which is equal to x squared, if we're to find f of 2, we're just putting 2 where x is, right? So it's same applies if you're now finding f of g, we're now putting g wherever x is, so it will be g squared. So what it means is, we'll be just saying, what is our g now? We get x squared plus 1 squared. So it will just give us x squared plus 1 squared, which is equal to x to the power of 4 plus 2x squared plus 1. This is what you get. So the same applies on g of f. G of f, this one. If we were to find g of 2, we could have said, so our g is x squared plus 1, so you could have replaced x with 2 and say x squared plus 1. Same applies with g of f. G of f, we are just putting f squared plus 1, which is giving us what? Which is giving us what is f equal to? F is equal to x squared. So x squared plus 1, which is equal to x to the power of 4 plus 1. Just on functions, let's now talk about bijection, injection, and surjection. Right. The classes of functions may be distinguished by the manner in which arguments and images are related or mapped to each other. A function f which maps x to y is injective 1-to-1 if every element of the range corresponds to exactly one element in its domain x. So every element of the range corresponds to exactly one element of the domain. So which is, if we are talking about injection, we are talking, we first pick an element which is in the range, and we ask ourselves if that element if that element is corresponding to exactly one element in the domain. So like we have an element, let's say y here. So we ask ourselves, we tag this y and ask ourselves, is this y corresponding to one element in the domain, right? But for us to now work on proofs of injection or one-to-oneness, we have to consider the following definition. For xy in x, f of x is equal to f of y implies x is equal to y or equivalent. So what we mean is if we have our f of x being equal to f of y, right? This should imply that x is equal to y. I'm going to consider an example below which is going to show you what we mean by this. Or you can use the converse, which is for all xy in x not equal to y implies f of x is not equal to f of y. An injective function is an injection. That is the other one you can consider. So show that the function f of x is equal to 2x plus 3 and g of x, which is x to the power of 3 minus 2, are injective. That's that's what so show that the function f of x, which is equal to 2x plus 3 and g of x, which is equal to x to the power of 3 minus 2, are injective. So for us to show that, we have to start from f of x being equal to f of y, and it should give us x is equal to y. So in this case, our f of x is equal to 2x plus 3, and our f of y is equal to 2y plus 3. So which is, if we equate f of x to f of y, we get 2x plus 3 is equal to 2y plus 3, which we give, if we subtract 3 from both sides, we get 2x is equal to 2y, which implies that x is equal to y. Just as in the example, usually if we are not using x and y, because sometimes using x and y might confuse people, so we can just use this one alternatively. F of x1 equal to f of x2 should imply x1 is equal to x2. So which is, for this case, we'll be saying, let's just consider a new function. Let's consider g of x, in fact. So g of x1 would be equal to x1 to the power of 3 minus 2, and g of x2 is equal to x to the power of x2 to the power of 3 minus 2. So from our supposition, we have to suppose that g of x1 is equal to g of x2. We are required to prove that x1 is equal to x2 from that. So if we suppose this, we can use it, right? So we have x1 to the power of 3 minus 2 is equal to x2 to the power of 3 minus 2. So we have to clear 2 from both, minus 2 from both sides. We just have to add 2. So we get x1 to the power of 3 is equal to x2 to the power of 3. And if you put cube root both sides, will give us x1 is equal to x2. So from our supposition, g of x is equal to g of x1 is equal to g of x2 implied that x1 is equal to x2. Therefore, g of x1 is equal to g of x2 implied that x1 is equal to x2. Therefore, the function is injective. So you can test some functions whether they're injective or not using this very method. I'm just going to consider also a function which might prove to be not injective. Okay, so let's consider a function like just for the sake of understanding. So let's consider our f of x, which is equal to x squared plus 1. So prove that f of x is not injective. Right. So f of x is not injective, right? So we have suppose that, or assume, right, f of x1 is equal to f of x2. Right. So we are supposing that f of x1 is equal to x2. Thus, f of x1 is equal to x1 squared plus 1, which is equal to x2 squared plus 1, which is equal to f of x2. So just maybe to split it so that I understand if you combine this, some people end up confused. So let's say thus f of x1 is equal to x1 squared plus 1. F of x2 is equal to x2 squared plus 1. So what it means is this one is, if this one is equal to that one, we are supposing that this one is equal to that one. That's x1 squared is equal to, that's x1 squared plus 1 is equal to x2 squared plus 1. So what it means is we have x1 squared is equal to x2 squared if we subtract 1 from both sides, and then the square root will give us x1 is equal to plus or minus x2. So if x1 is equal to plus or minus x2, it means that this one is not injective always. It can be conditionally injective when we say we are considering the positive square root only. Like what I mean is, yes, since we have put in the square root here, if we consider positive square root only or negative square root, it will be injective. So if something is conditionally injective, it's not entirely injective. So like if it is injective on some parts in R, we cannot say it's injective in R, right? So you have to put the condition for it to be injective. Then lastly, we're going to talk about a function af for which maps x to y is called onto if for all y in y there is an x in x such that f of x is equal to y. So this one is now an ontoness or surjectiveness. So surjectivity means that for every element which is in the range, like for every element which is in y, there should be a pre-image. There should exist something it came from. So what we are just saying here is for every output, there should be an input. That's what we mean by surjectiveness. We cannot have an output without an input. That is what surjective means. For every output, there should be an input. Be it like 2 inputs, whatever, we don't care about how many inputs we are put there. But then, like, for every input, there should be an output. I don't know, for every output, there should be an input. That is surjectiveness. So you can actually see from this example that show that f of x is equal to 3x minus 5 is onto. What we first to do is we should first to make x the subject in this equation. So we have x being equal to y plus 5 over 3. And f of y plus 5 over 3 will give us 3 by y plus 5 over 3. Oh, sorry, just to take you back a bit. We have x is equal to y. I said we first make x the subject, right? If we make x the subject, we then substitute this guy here into f. So that guy is y plus 5 over 3. We substitute them into x. So if f of y plus 5 over 3 is equal to 3 by y plus 5 over 3, minus 5, which just gives us y. So what we just realized here is for every value of x, there is a value y. For every value of y, there is a value of x, which makes it possible. Therefore, f is onto. So just for practice of this concept which we talked about, I've set some tutorial questions and tutorials after continuity. The next video is going to be talking about continuity. I'll send it tomorrow. I'm going to split it with this one so that to avoid long videos. So generally, since we talked about bijection and injection, let's a function, if a function is one-to-one and onto, it's called, it's a bijective function. If it is injective and surjective, it's called a bijective function. That is, if a function is both one-to-one and onto, then it's called a bijective function or a one-to-one correspondence. Okay, guys, on the inverse function, these ones are just done on the previous course, so just make sure that you read these other parts of the notes. The next chapter would be chapter 3, limits and continuity. Thank you.